Okay, we're going to do some videos about the integrating factor and linear ODEs. So what we want to do is start with a linear first order ODE. Like this. We want to get to a directly integrable ODE like this. We want to get from the directly integrable ODE to our solution. Which turns out to be this. Like so, right? We want to be able to go from here with this integrating factor called R and then we get to a solution like this. The price we pay for this is that the integrating factor is quite unfortunate. It's the integral of p inside an exponential. So that's quite a tricky function to deduce. But this is the idea of solving first order ODEs with the integrating factor. We're going to see where this integrating factor comes from, right? So we're going to look in this big gap in here. So we start at our linear equation. We end at our directly integrable equation. And we target R. We can use the product rule to expand this. So we differentiate the first one, leave the second one alone. Differentiate the second one, leave the first one alone. Now, we can kind of see, we know that we want this to look like where we started. So if we want to get these r's in place, that one and that one, we can multiply this equation by r. Okay. And we can now compare, right? We've got this term, and we've got this term. So I need to distinguish them. Right, so the only term that we haven't got yet is this one, right? But we've got something that looks kind of similar. We need to compare these two terms. If our equation is to be true, if we are to get what we want, we need y times dr dt equals rt pt y. If we're to get what we want, this equation must be true. The y's cancel. And we have a separable ODE. Now that's great because we know how to solve separable ODEs. We got dr dt is rt pt. All right, so we've got to put the r on the left-hand side and we've got to put the t on the right-hand side. We do our normal, separate and integrate. We get a log. And there's nothing we can do with this equation, right? We're not given an explicit form of P of t, so we have to leave it in this integral form because we can't go any further. We can, however, deduce that r, our integrating factor, exponentiate, deal with the plus and minus. We can put a plus c here. Let's just put a plus c there. But we'll discover that it becomes irrelevant later. So that's what happens to our constant of integration. Now I'm going to claim equals 1, but we'll see why we can do that later. We'll write A for now. So what we've got is we've deduced this magical value of R that lets us go from this linear form here to this directly integrable form here. Okay, so we've moved from step 0 to step 1. So that's our canonical equation. We multiply through. We use the result that we worked so hard to get. Between steps 1 and step 0 and 1. Now, if we are to write this out explicitly, we have this, and now we see that A is a common factor on both sides. So irrespective of what value A happens to take, this equation is true. So we can do what we said, right? We now understand that we can just set A equal to 1 and ignore it hereafter. What we have now is this is directly integrable. So we're now at step 1. And we're moving to step 2. We integrate. Integration inverts the differentiation. So we can write e to the p t dt times y equals the integral of e to the integral of p t dt times q of t dt. Doesn't matter that these are awful functions. If we want, we can just write this if we wish to disguise what the integrating factor happens to be. So it becomes a simple task to rearrange this for y, our solution. Now, it's often worth remembering that this integral yields a constant. And so we can put it there. All right. It's not actually necessary. We just have to remember, it's not actually necessary to write it in this form. It is necessary, however, to remember that every time we solve a problem with this, we get this constant. In a later video, I will summarize the steps that are required to solve a linear first order ODE.